Hi guys, welcome back. So today we're looking at constructing and using graphs. So we're going to season our graphs using the SALT method. My sister came up with that one. I really like that analogy. And we're going to interpolate or extrapolate data from a graph. So this is actually stuff that's really useful in maths as well. And I've actually done some videos on some of the topics that are in this video, also in my Year 10 Specialist Maths playlist. So if you wanted to check out like more about line of best fit and correlation, I would jump over there. There is a video on that. And there's also a video on interpolation and extrapolation, and it might even be the same video. Can't remember off the top of my head. All right, so key ideas. So we're going to be constructing graphs and using them to communicate, solve problems, and to make predictions. So how do we draw a graph correctly? And I'm just going to write this little acronym that I had from before. So my sister came up with this one, SALT. You're going to season your graph. So the first thing you're going to do is you're going to sketch each of your points. So sketch your data, and you're going to do that using X as your dependent variable and Y as your independent variable. So I might write that up here. So X and Y, the first one is your independent variable, and then the second one is your dependent variable. So just as a refresh, the independent variable is not impacted by the dependent variable, but the dependent variable depends on the independent. So for example, if I was measuring the growth over time, how tall a plant is not going to affect the time of how long it's been growing for, but the time for how long it's been growing for will affect how tall it is. So the independent variable would be the time, and the dependent variable would be the growth of the plant. And so usually, unless you're like in physics or something like that, the independent variable is going to be time. And so the time usually is going to go along this x-axis here. All right, the next thing that I've got is axis. So what do I mean by axis? I mean that you've drawn your x and your y axis, and you've got the name of the independent variable here on the x-axis, and you've got the name of the dependent variable on the y-axis. Labels. So really important that you label your graphs. Oh, sorry. And with axis, I should mention as well, that includes putting number values on your axis. So if you haven't put numbers here and you haven't put numbers up here, you've done the wrong thing. So labeling. So you have to label each axis, so time and temperature, and we've used the units in brackets. So please make sure, for example, if you're measuring something in seconds, that you would put time and then seconds in brackets, so that I would know, for example, for some sort of experiment that you be, running for term 2 for your assessment. Hint, hint. Excuse me. You need to make sure that you label each line, or you have some sort of key that tells you what information is. So these crosses represent the distilled water and the circles represent the honey. Typically speaking, with scientific graphs as well, it's better that you use different symbols for each variable rather than different colors, because when you print stuff out, it prints out black and white and you can't actually tell what the difference is. Also, if you have someone who is colorblind who is trying to read this graph, it's not always easy for people to distinguish between different colors. And so it's going to be a lot better scientifically when it's just the symbols that you're changing. And I can show you how to do that in Excel when it comes to doing our assessment. We've also labeled our lines of best fit here as well. Okay, and the last thing we've got to do is the title. And when we're writing the title, we always have to include both variables, and it doesn't have to be anything crazy. So for us, on our x-axis, we have our dependent variable, which was the time, and then our y value, which is our dependent variable, it is the temperature. So I need to mention the independent and dependent variable in my title. So how time affects temperature, or something like that, right? So how does X affect Y? So this graph, they've just got the change in temperature of honey and distilled water over time. So that's another way that you could do it as well. Okay, so just make sure we're mentioning both dependent and independent variables. And then the very last thing, and no one ever does this, so you've got a label, and with figures, so with graphs and things like that, it goes on the bottom. With tables, it goes on top. The title goes on top. And then there's just like a 1-sentence description. So this literally could just be, this graph shows the change in temperature of honey and distilled water over time. Okay, so that's all you have to do. I'm a bit particular with these graphs. I'm going to talk to you more about like how I like to to graphs because there's something I don't like about this graph. So when we go to do our experiments and our assignments, I will show you specifically the way that I like my graphs to be done. Okay, so a scatter plot is basically it's just like a bunch of dots, right? And each of these dots represent the coordinates of our independent and dependent variables. So for example, I would read this scatter plot as this temperature is about, let's say about 2, and then it yields about, let's just say about 6% yield when it has a temperature of about 2 degrees. And each of these little error bars, we've got an error bar now in the X and the Y direction because with the temperature, we know that there's going to always be some sort of error or some sort of uncertainty associated with each of our measurements. So for example, if we had a thermometer and the smallest increment on the thermometer was 0.1 degrees Celsius, then we know that our absolute uncertainty would be plus or minus 0.1 degrees Celsius. So they've just indicated that on the graph using error bars. Similarly, they've done the same thing with yield. So you might have a percentage yield, and again, with some level of precision and accuracy, you might have like plus or minus 0.1% yield. Okay, correlation. I'm going through these pretty quick because a lot of these we've done before. And again, I do have some information on correlation in another video if you want to check that out in more detail. But let's talk about line of best fit first. A line of best fit, I'm basically just going to try and draw a line through each of my graphs, and I'm going to try and touch as many of these data points as I can. And if I can't, touch every single data point, that's okay. I'm just going to try and do the best job that I can to get that line of best fit. And if there is a few issues, we'll just try to make sure that there's roughly even numbers of dot points above and below that line. So when I'm talking about correlation, the relationship between the X and the Y, or the relationship between the independent and the dependent variables. And so we can see that for some of these, they have a pretty high correlation. Their line of best fit is either describing them incredibly well, or it's describing them okay, it's okay. In my other video that I mentioned just before as well, correlation is not the same thing as causation. So if I talk about correlation versus causation, really what I'm saying is just because two things seem to fit a particular pattern very well doesn't mean that one necessarily causes the other. So perfect example, the stock market, when the stock market crashes, the price of everything crashes. So the price of apples is actually really well correlated with the price of the stock market of the Dow Jones. But the price of the apples does not cause the price of the Dow Jones just because they're well correlated. In fact, it's the other way around. So we always just have to be kind of careful and considerate when we're thinking about these sorts of things. Okay, so let's do an example. So a student measured the amount of product produced from their chemical reaction and plotted the data on the graph in figure 4. Draw a line of best fit for this data. Calculate the amount of product that would have been available at 5 minutes and 30 seconds. So line of best fit, I'm just going to do my best job that I can. I'm going to try and catch as many of these points as I can. And if I can't, I'm going to try and make sure there's about equal numbers of points above and below that line. This one looks like it's going to be a pretty strong positive correlation. When I say a positive correlation, what I mean is that as X is going up, Y is going up as well. If it was a negative correlation, as X goes up, it would mean that Y would be going down. So this is a positive correlation. Calculate the amount of product that would have been available at 5 minutes and 30 seconds. So this is a form of interpolation. So interpolation just means that I am making a prediction within the range that I've measured. And the only way that we can accurately make predictions is through interpolation. Extrapolation would be like I'm measuring something outside of the measured range, and therefore it's not going to be accurate. So we're going to interpolate this data. So we would get a line, and I'm going to draw that roughly at 5.5 minutes. And again, I'm just going to look on my y-axis here, and where does that sort of correlate on my y-axis? So that's going to be about 5.5 grams of product that would have been available at 5 minutes time. That easy. Okay, so let's jump in. Let's do some questions. So define causation. Causation is when something causes something else. Correlation is when the two variables are well matched to each other. So we could have a positive correlation. So that means as one goes up, the other is going up as well. Or we could have a negative correlation. So as one goes up, the other goes down. Outliers, they're just those weird values that don't seem to make sense, and that could be as a result of some sort of systematic error or some sort of ID10T error. If you don't know what I mean by an ID10T error, maybe write it out and see if you can guess what I'm trying to say there. Okay, let's have a look. Describe a situation where a bar or column graph should be used. I'm a chemist, in my opinion, never. But bar or column graphs are generally used when we're dealing with qualitative data. And we're looking at the numbers of things, for example. Explain why a scientist should not ignore an outlier when graphing or discussing their results. Because it could be valid. I mean, we just have to mention that, you know, it's done something weird, and it could be that the machine was off that day or whatever. Most of the time, scientists do actually discount these outliers if it's an obvious outlier. Like if it's a machine error, we know it's a machine error, and so there's no point including that in our values. Okay, here's the good stuff. A chemistry class sets up 2 test tubes, each containing identical amounts of hydrogen peroxide, H2O2, and manganese oxide, MnO2. A chemical reaction occurs that generates oxygen gas according to the following equation, and the textbook does not actually have the equation. So I'll write that for you and I'll balance it and I'll come back. As I was going through, I just realized this question has actually got it. It's just popped up over here. Okay, so this is our balanced equation, and these are all our values, our amount of oxygen produced in mils at particular times. So determine the volume of oxygen produced in the reaction of test tube 3 at 3 minutes and 30 seconds. So what we would do is we would graph this using our scatter plot. So we would have the independent variable. So the independent variable would be the time. So X is going to be the time. And again, we would write that in minutes. So making sure we put our units there. Our dependent variable, our y-axis would be the amount of oxygen produced, and that is going to be in milliliters. Okay, so then we would plot that. And then with this, we can see we've got our little error bars. So just to show you, for example, this would be at 1 minute time, and this would be our value for 1.4. So we would do our point there, and then we would add 0.2 to get the top bar and subtract 0.2 to get the bottom bar, and just do the same thing for every single one of the points. Then once you've done that, draw your line of best fit, use that same method as before to predict the amount, and again it has to be done through interpolation, so within that measured range, and then we should be able to find the value of the oxygen volume at 3 minutes and 30 seconds. So I'm not going to go ahead and do that. I think this is pretty straightforward. We've done graphing a whole bunch. If you do still have issues, do go and check out those other videos that I have up in my Year 10 playlist, and do email me if you are still struggling. Alrighty guys, I'll talk to you again soon. Have a wonderful day.